Starting from the easy problems, so here is we're going to calculate, determine is the Kepler's the time of flight is simply what we defined in that graph is simply we want to determine delta t. Okay, so this one basically is again is the easy one. So again here we given the true anomaly and we're going to find the time of flight delta t. So this one can be easily done by this. We can find out what is the Kepler's third law here. For Kepler's third law is this: we have our orbit, and this is our occupied focus, and Kepler's law saying at a given constant interval of time, the area being swept by the moving object is the same. So that means we can predict this area, for example, let me call this area is A. And the time spent from here, from T0 to here is T0. Let me put it into the simplicity, say starting is 0, and to this point, say time of flight is delta t. To the next constant interval of time, so say moving to here is 2 delta t. So basically the traveling time from here to here, delta t, from here to here is 2 delta t. The area, so this area must be the same as A, right? So that means here basically is we know the dA dt is constant. And that's Kepler. And for this one, we simply derive from here. And this chapter will begin with how to extend from this and get into more useful information. Okay, so keep those things. We will base upon this and begin to formulate the Kepler's problems. So from here we first we introduce formulate the Kepler's equations. So the Kepler equation, the goal is to determine the relations between delta t, time of flight, nu, the true, I would say the angular displacement on orbit. Okay. So again, this is our orbit, and this is the occupied focus here. So this is perigee, and this is at time t, and at time t equal to 0, which simply take our reference starting from 0. Okay, so here this is the swept area. and let me call this area is A1, and this is the true anomaly nu. Okay, and we know for period of orbit we define as t, and for this one, say for example for this orbit we know the semi major axis is a. So in this way, t we can express is by a cube of mu, right? Hopefully that is right. Yes. Okay, and so we let the t is basically starting from here to here. That is the time of flight we spent. So t is the time of flight. So again, we utilize this information. So the t, the time of flight between the perigee, that is where we're starting from our measurement of the time swept, the area sweeping informations. So here, that is perigee. Or sometimes people, I think that sometimes people say t minus t0. Really depends on how the symbol you like. Okay. So t divided by, that is the time spent from here to here compared to the whole cycle. How about this? And let me give a p means the period. Okay, so tt, not to confuse with other symbols. So again, we utilize Kepler's third law to make the whole cycle, and that means we swept. The area being swept is the whole area. The area of the of an inlet equal to pi AB, and A is the semi-major axis, and B is the semi-minor axis. If you keep this kind of information, so that is pi AB. And in the time of flight for this period, that one is, in terms of the symbol, that is A1. That's it. Right, so from here you can see it's pretty easy. So for example, right now we are given nu. Looking at this problem definition, that means if we given nu, that means we know the piece of the pi, a piece of this kind of the oval-shaped pizza, how big the size you're going to share. So that means we given the nu, then imply we will be able to calculate this area. So that means the A should be able to measure it. So divided by the whole area, then we can easily calculate, we can determine T. So basically T is a certain portion of the period. That portion is given by this. So that is the easy formulations of the Kepler's problem. Okay? So again, the delta T means simply is the numerator here, that is the time of flight between the destination and the reference point. Okay? So in concept, this is pretty straightforward. And pi AB, that is given because A and B are the orbital elements, so we should be able to determine it quickly. So now the issue is how can we detail the calculation for A1. And so here we'd like to spend a couple minutes about this. Keep this one in mind, and then I don't need this anymore. Let me erase this. So that means T can be found as long as A1 is determined. Okay, so right now how to determine A1? A1 is the area being swept by the objects on the orbit. So to do this one, we, starting from here, I will draw the orbit, and upon the orbit, I'm going to draw additional circular path. So that one. So this is the orbit. So this right now I'm drawing is the semicircle. Okay, so this is a circle of radius 8. So basically here we're using the semi-axis to draw a circle. I think that's a more realistic. Okay. So this is the focus here. So if we know, say here we are given, for example here, assuming we are given the orbital elements, say A and E, okay? So we know the semi-major axis, we know eccentricity. And now even we know, say, the satellite, say satellite is moving counterclockwise. So this is our set object here. So here, this is new, we are given. So right now our job is to find what is A1 here. Okay, so focus on this one, then A1 I can do a little bit the geometry to see what happens. So for this case, let me passing through this object, I draw a vertical line. Okay, I draw a vertical line, so here is this. This line is 90 degrees to here. I simply draw additional information. So from here, I connect to, so basically corresponding the point, the projections of the set to the circular is there. So from here, I'm connecting to the center here. So let me draw a line here. Okay, so that I'm connecting to here. Okay. So from here, we can do something. So under this case, I simply use our textbook notations. So corresponding angle here and textbook is using E. And E, there's a name for the eccentric anomaly. Anomaly, that means angle. Okay, and that's a name. And we're going to turn out is the new, our true anomaly can be related to this eccentric anomaly in certain way. So I will give that relation to you quick later on. Okay. So now we have A1. So simply A1 can be found is in a certain way. So let me give certain notations here. So this triangle is, let me call A2. Okay, this little triangle is A2. So basically the A1, A2 has relation is this. So this is the circle. And for circle, that has the equation x squared plus y squared equal to a squared. For ellipse, we have these equations. Okay, so basically here that is I redraw that shape into here. I don't want to mess up. So basically this is the semi-major axis. Okay, the center like that one. So right now, I want to, before we answer this question, what is the A1, we look at here. And let me put out two areas. This area is the area corresponding to, let me get rid of this one. This area is corresponding to the shape, that one on the ellipse. And this area is corresponding in circle. Okay. And the ratio of the two areas, so let me say this is the area corresponding to circle, and this area slash area here, let me highlight this one. This is the area corresponding to ellipse. From here you can see basically that is the ratio between the y-axis. They have a common x-axis. So if you remember earlier we've shown this one before. For circle we have is y equal to squared x squared minus a squared. Okay, and for corresponding to the ellipse, and here we have information is y equal to b times 1 minus x squared a squared. Okay, let me rewrite this one. This one basically is b times a squared. Oh, sorry, this is a squared minus x squared. So this a squared minus squared divided by a. Okay, so this is the y on the circle. This is the y on the ellipse. So basically from here you can see the circle, if we fix the base, then the ratio on the ellipse with respect to the y on the circle basically is b over a. Okay, so we take up this ratio, then from here you can see this is a1 plus a2 is the piece that corresponding to on the ellipse. And on the circle, that is this big piece. Okay, so from here we can have a little bit more information. Let me keep to here. So that means, so therefore, a1 plus a2 will be equal to, what is this a circle corresponding to that one? That will be corresponding is, let me give a notation here. So here is Q, and this point, let me call it Q. This point is, let me call it S, and this point, let me call it V. Okay, so A1 plus A2 simply is the area Q as V, and Can you see it? The area QSV. The area QSV simply is the formulation on the A circle here. Okay, with respect to, right now we're going to calculate on the corresponding portions on the ellipse. That is A1 plus A2. So we have this relation. And what is these portions? Area QSV basically is this piece of the pie minus this triangle. Are you able to see it? Again, right now the QSV is this area. Okay, I kind of encounters along the parameters of the QSV. This one basically equal to this pi minus this triangle. Are we okay? Then you give a notation here. So basically that one equal to, for given pi, this piece of the pie, that is how much? That is equal to the angle E in terms of radian divided by 2 pi times pi a squared. So again, this is the portion of the pie. This is the portion of this pie. Got it? And minus the triangle and OQS. Are we okay? Any questions about this? It's okay, right? Okay. So here is totally pure geometry. So now our goal is to calculate A1. So what is A2 here? So A2 here, basically A2 is this triangle here. And this height is how much? So here I want to formulate what is A2. A2 simply is equal to half of the base multiplied with the height. What is base? And the base simply is this distance here, right? So everyone look at here. So the base is simply this distance. So this distance simply is base. And we know A and E are given, so the distance between the focus to origin is AE. Okay, so this distance simply is equal to this distance simply is equal to AE minus this portion. Got it? Right now we're looking for this one. This portion is the whole length multiplied with this one. And this portion is A times cosine E. So that is AE minus A times cosine E. That is base. Again, right now we're looking for this piece. That is the AE minus this one. Got it? Okay, now we're looking for height. The height is this one. Okay, so this is the height from here to here. And again, this portion, this height is a portion of the corresponding circle and multiply with B over A. So right now it's B over A multiplied with corresponding the portion on the circle, and this circle is A sine E. Are we okay? Good? Okay. So with everything together, and we simply just using the pure geometry, so A1 is here. And let me give you the A1. So A1 is equal to AB. We after simplifications, and E minus E sine E. So this is our A1. Okay? And once we found the A1, we simply plug in here. So therefore, and we can plug in here. So therefore, let me rewrite that equations and to simplify into the Kepler's equations here. So by plugging into that equations, T minus 0 divided by Tp equal to A1 pi AB. And we have is this. So here, Tp equal to our period 2 pi A cube over mu. Okay. So here we have is simply T will be equal to simply plugging. So we just do it. Okay. So that is Tp 2 pi A3 mu times A1 AB over 2 E minus E sine E and divided by pi AB. So therefore T is equal to A3 over mu E minus E sine E. This is Kepler's equations. Yes.
So that's being given in an angle then?
Angle, yes. So right now, what is E? E is the angle, right? E is the angular displacement, that's the angle. And Kepler's equations is described in terms of E, not in nu. And see, the nu is a true anomaly, that is a part of our orbital element. However, in this equation, we derive in terms of E. Little bit inconvenience. So actually, in terms of the more practical, we have to convert E in terms of the nu. So one more step will be making this one more applicable for our the orbits, right? Okay. But anyhow, we're almost there. And the note. So here, before we proceed, I give a little bit more notes. So here, the A is the the AE are given, are the orbital elements. So two of the orbital elements. So by all means, you have to first calculate A and E to know the orbits, what kind of orbit you work on. And nu is the gravity constant, that can be the constant, you simply do it. So E, again, E is the eccentric. Okay, and which can be related to nu, true anomaly, nu. And this one we will be we will leave it derived, don't worry. Okay. The third one, I'm going to introduce to you common notations. And this notation is not that useful, but just to complete and with your readings. And sometimes we rewrite these equations into this. By defining the two terms, one is called the m, defined as the e minus e sine e, and we define the n equal to mu over a cube. Don't ask me why, I just try to complete the whole note taken. So here we can rewrite these equations as this NT equal to n. Okay. So sometimes people like to take out this format. It's not very practical, but just for note taken, just get familiar with the notations here. Okay. And the original is this one. So from here, in this way, we can see what is the easy problem, what is the hard problem. Again, the easy problem of the Kepler equation is this. Easy problem is this. We are given E. T. Right? T is a time of flight. Here the T, if you like, you can add it up one more, say another point here, whatever they want. The T is time of flight. Okay. So easy one is this. As long as we know the E, we simply punch calculators. Sine E multiply with eccentricity, and with this one, and T is done. That's only a few seconds. And for this case, in this way, I would say E is in radian. If you like, E is in the unit of radian. This is important, okay? In these formulations, you have to convert E in the radian. And so under this case, you can see the hard one is this. We are given T and solve for E. So for this case, if we know the value of E, the T, and we solve for E, this is the hyperfunction. So that involved is the, I don't know how to solve by hand. Okay, so that is a hard one. The hard one is the hard in terms of the computational rigor. Is that meaning the hard in thinking or in mathematics? No, simply means the easy or hard simply means in terms of computational rigors. Okay, and this one in terms of the computational science, they call the rigor of the zero and zero problems, and this one sometimes they classify as an MP problem, and that's the terminology in terms of computations. Okay, so again, this one we're going to involve with the numerical method. So so right now the remaining to finish these sections. And what I need to give to you is this one, how to collect. We have one more small sections, one more small notes before we close in this section. Now the question is this. How to relate E to mu. Let me give you the result first, and if we have time, then we'll do it. This one is this tangent mu over 2 equal to 1 plus E, 1 minus E, tangent E over 2. How about get rid of the parentheses? Okay, so this equation provides us the relation. and converting between the true anomaly and the eccentric anomaly. So once this one, you combining the two equations together, we have the whole story. We know the angle of the true anomaly, we can predict time, or vice versa. And this equation is not provided by our textbook. And our textbook versions is this. I won't recommend, but let me give that to you. Cosine E equal to E plus cosine mu. This is our textbook version, and I won't recommend you use this one. Why? The reason? Again, this one involving, if you want to do that one, you're going to involve the arc cosine. And arc cosine, again, that is a problem like this. This is the sinusoidal function. So this is theta. How about this? This is E. Cosine. This is pi over 4, pi over 2, and 3 pi over 4, 2 pi. No. Half it. Okay. So, for example, if we know, for example, if we know the nu, then we know the cosine E equal to certain numbers. So, for example, say the cosine E equal to this number here. Okay. So, for example, if we know this number is equal to E plus this one, whatever the number, any number, we want to solve for E. So basically, you wind up is posing you two options. One is this value. One is this value. Let me call the E1. Let me call the E2. Okay. So which means this one is we given nu and given E, and from here this value is equal to E plus cosine nu and 1 plus E cosine nu, right? So if we know these things, then wind it up, once you punch your calculators, you have to make a decision which value of the E is correct. It's kind of bothersome. Any answer or any good suggestions for making the decision which E1, E2? Throw the dice, that could be half-half. Okay, and the best way is you simply put into your graphics, and you know your problem is, and your problem you could be winded up is this, the E1 could be something corresponding in the two symmetric positions. Graphically, that will help you to make a right decision picking up E1 and E2. You have to do this every time. And this one is not so reliable. And this is a solution provided in our textbook. And I feel this is not good. And so I dig out from the other textbook, and we're using this one. And the one is this. And why this is good? Because this one we're involving is tangent. What is tangent? Tangent curve is this. This is theta. This is tangent theta. And the tangent basically working on the single value for a single value problem of the tangent that is from pi over 2 to pi over 2. And right now we simply take a half of the E. So basically say theta equal to half of the E. Then in this way the E, this one tangent basically involves the E is in the range of the minus pi to pi. Basically that covers 2 pi regions. So basically, the single value problems from these functions cover the whole domain we need. So I would recommend using this one. You right away, whatever the punch from your calculators, that will give you the right answer. And you don't need to make a decision for which one you go. Because this one is guaranteed. This is a single value mathematics. This one is a multiple value mathematics, and this is bothersome. Okay. So I would recommend using this one. And maybe if we have time, then I will explain to you and for this one. But here, because we won't recommend using this equation, I would say we simply just take up this one, okay? And get this one will involve quite a bit space. I would kind of choose to skip off that one. We simply take it up. Okay? Okay, so today we have going to lay the base, and next time come back we have a more kind of the numerical calculation.